centuries, humanity has gazed at the night sky, wondering if other worlds exist beyond our own. The idea of planets orbiting distant stars is not new. Ancient civilizations speculated about the existence of other Earth-like worlds long before modern science provided proof. Today, we call these distant worlds exoplanets, planets that exist outside our solar system. Their discovery has reshaped our understanding of the universe and our place within it. Long before telescopes, philosophers, and astronomers pondered the possibility of other worlds, the ancient Greeks, including philosophers like Democritus and Epicurus, believed that countless other worlds must exist, some even resembling Earth. Meanwhile, Hindu, Buddhist, and other Eastern traditions spoke of infinite worlds within the cosmos. During the Middle Ages, scholars like Giordano Bruno proposed that the stars in the sky were distant suns, each with their own planets. This idea was considered heretical at the time, as most people believed Earth was unique. But as science advanced, so did our ability to search for these worlds. By the 17th century, astronomers like Christian Huygens and Isaac Newton speculated that planets might exist around distant stars, but without observational proof, these ideas remained theoretical. In the 19th century, astronomers made their first attempts to detect exoplanets, though their tools were too primitive to confirm any discoveries. Some scientists claimed to have found evidence, but their findings were later disproven. The true search for exoplanets would have to wait until the age of modern telescopes. For much of the 20th century, finding planets around other stars seemed impossible. The vast distances between Earth and other stars made direct observation extremely difficult. The biggest challenge was that stars are millions of times brighter than the planets orbiting them, making it nearly impossible to see exoplanets directly. Astronomers tried different techniques to detect exoplanets indirectly. One of the earliest serious attempts was in the 1960s, when scientists studied tiny movements of stars, hoping to detect the gravitational pull of an unseen planet. However, technology at the time was not advanced enough to confirm these observations. Everything changed in 1992, when astronomers Alexander Wolszczan and Dale Frail made a groundbreaking discovery. They found the first confirmed exoplanets orbiting a pulsar, a rapidly spinning neutron star. These planets, known as PSR 1257+12, were completely different from anything in our solar system. This proved that planets could form even in the most extreme environments. Then, in 1995, another breakthrough occurred. Astronomers Michel Mayor and Didier Queloz discovered the first exoplanet orbiting a main sequence star, a sun-like star. This planet, 51 Pegasi b, was a gas giant, similar in size to Jupiter, but much closer to its star. This discovery revolutionized astronomy, proving that exoplanets were not just possible, but common. As technology improved, astronomers built more advanced telescopes designed specifically to detect exoplanets. The Hubble Space Telescope, launched in 1990, provided some of the earliest direct evidence of exoplanet atmospheres. However, the biggest leap forward came with the launch of NASA's Kepler Space Telescope in 2009. Kepler used a technique called the transit method to detect exoplanets. It monitored the brightness of stars, looking for tiny dips in light caused by planets passing in front of their stars. This method led to the discovery of thousands of exoplanets, including rocky planets similar to Earth. By the time Kepler ended its mission in 2018, it had identified over 2,600 confirmed exoplanets and thousands of additional candidates. This telescope transformed our understanding of planetary systems, showing that almost every star in the galaxy is likely to have planets. The discovery of exoplanets has profound implications. First, it confirms that planetary systems are common, suggesting that the Milky Way alone could contain hundreds of billions of planets. Second, it raises the possibility that some exoplanets might be habitable, capable of supporting life. Scientists are especially interested in finding Earth-like planets in the habitable zone, the region around a star where liquid water can exist. So far, several promising candidates have been identified, including Kepler, 22b, Proxima Centauri b, and TRAPPIST-1d. These discoveries bring us closer to answering one of humanity's oldest questions. Are we alone in the universe? Astronomers use several methods to find and study exoplanets. The transit method is the most successful technique, used by telescopes like Kepler. It detects planets by measuring dips in a star's brightness as a planet passes in front of it. The radial velocity method detects small movements in a star caused by the gravitational pull of an orbiting planet. This was the method used to discover 51 Pegasi b in 1995. In rare cases, astronomers can directly photograph exoplanets using advanced telescopes that block out the star's light. Another method, gravitational microlensing, relies on the bending of light due to a planet's gravity. It is useful for detecting planets that are far from their stars, or even free-floating planets. Each of these techniques has helped expand our knowledge of exoplanets, and future missions will refine them further. The discovery of exoplanets is one of the most exciting scientific advancements of our time. It has reshaped how we view the universe and our place in it. With thousands of exoplanets already confirmed and many more awaiting discovery, we are just beginning to explore the vast diversity of worlds beyond our solar system. As technology advances, we may one day find the ultimate discovery, a planet that harbors life. This marks the beginning of our journey into the strange and fascinating world of exoplanets. In the next section, we will dive deeper into the many types of exoplanets, from gas giants and lava worlds to water planets and rogue wanderers. The diversity of exoplanets is far greater than what we see in our own solar system. While we are familiar with terrestrial planets like Earth and Mars, gas giants like Jupiter and Saturn, and icy bodies like Neptune and Uranus, exoplanets come in an incredible variety of forms, many of which have no direct counterparts in our system. These distant worlds challenge our understanding of planetary formation and the conditions that make a planet habitable. One of the most common types of exoplanets discovered so far are gas giants. However, unlike Jupiter and Saturn, many of these exoplanets orbit extremely close to their stars. These are known as hot Jupiters. They are gas giants that experience scorching temperatures due to their proximity to their stars. The first confirmed exoplanet, 51 Pegasi b, is a classic example of a hot Jupiter. Some, like HD 189733b, have intense weather patterns, including violent storms and clouds made of glass particles that may rain sideways due to strong winds. Not all gas giants are hot. Some orbit farther from their stars and remain cold, much like Jupiter and Saturn in our solar system. These cold gas giants may have thick cloud layers, dynamic storms, and extensive moon systems. In some cases, they are much larger than Jupiter, earning them the name Super Jupiters. These enormous planets blur the line between gas giants and failed stars, as some may be close in mass to brown dwarfs. Objects too large to be planets, but too small to ignite into stars. Another class of exoplanets that has no equivalent in our solar system are super-Earths and mini-Neptunes. Super-Earths are rocky planets larger than Earth, but smaller than Neptune. Some may have thick atmospheres, while others could be more Earth-like, with solid surfaces and the potential for water. Mini-Neptunes, on the other hand, are smaller versions of our own ice giants, with deep atmospheres and possibly thick layers of water or ice beneath their clouds. Planets like Kepler 452b and Tauri 700d are intriguing examples of these types, as they exist in their stars' habitable zones, raising questions about their potential for life. Among the most fascinating exoplanets are water worlds, planets covered entirely in vast, global oceans. Unlike Earth, where landmasses break up the ocean, these planets may have no exposed land at all. The oceans on these worlds could be hundreds or even thousands of kilometers deep, with immense pressures creating exotic forms of ice at the bottom. Some candidates for water worlds include Kepler 1625b and GJ 1214b, which astronomers believe could be dominated by liquid water. In contrast to these aquatic planets, Some exoplanets are the exact opposite, lava planets. These are worlds that are so close to their stars that their surfaces are covered in molten rock. The intense heat from their stars keeps them in a constant state of volcanic activity, with rivers and seas of lava flowing across their surfaces. One such planet, K2141b, has extreme temperatures on its dayside, where rock vaporizes and falls as molten rain. These planets provide insight into how extreme heat affects planetary atmospheres and surfaces. Some planets do not orbit any star at all. These are known as rogue planets. Unlike traditional exoplanets, which are bound to a star's gravity, rogue planets wander through space, drifting in the darkness. They may have been ejected from their original solar systems due to gravitational interactions with other planets or passing stars. Without a star to provide warmth, these planets are shrouded in perpetual night, though some may generate internal heat from radioactive decay or a thick, insulating atmosphere. Scientists have identified rogue planet candidates such as CFBDSIR 2149 and OJUL 2016BLG1190, and some estimates suggest there could be more rogue planets than stars in the galaxy. Beyond these major categories, some exoplanets are even stranger. Some worlds may be composed largely of carbon instead of oxygen and silicon, leading to the possibility of diamond planets, planets where extreme pressures have compressed carbon into solid diamond layers. One candidate, known as 55 Cancri E, is thought to have a carbon-rich composition that could include vast deposits of diamonds beneath its surface. Others have atmospheric conditions so bizarre that it rains glass or metal. HD 189733b, for example, is a planet where high-altitude winds carry silicate particles, creating storms of molten glass that whip across the planet at thousands of kilometers per hour. Meanwhile, planets like WASP 180b have clouds made of iron that condense into liquid metal raindrops. The sheer variety of exoplanets has given scientists valuable clues about how planets form and evolve. While the planets in our solar system follow familiar patterns, exoplanets have revealed that planetary formation is far more complex than once believed. The existence of gas giants close to their stars, lava-covered worlds, and ocean planets suggests that planets migrate over time, shifting from their original locations due to gravitational interactions. Each new exoplanet discovery challenges our understanding of planetary science and forces us to rethink the conditions necessary for habitability. As more planets are found, scientists refine their models of planetary formation, learning how different compositions, atmospheres, and orbits shape the nature of a planet. Some of these discoveries may one day lead to the identification of a world that resembles Earth in all the right ways, a planet capable of sustaining life. As we continue our journey through the realm of exoplanets, the next section will explore one of the most exciting aspects of planetary science, the search for life beyond Earth. What conditions make a planet habitable, and how close are we to finding evidence of extraterrestrial life? Studying the atmospheres of exoplanets is one of the most important steps in understanding their nature and potential habitability. Unlike planets in our solar system, exoplanets are too distant to be observed directly in detail. Instead, scientists analyze the way light interacts with a planet's atmosphere to determine its composition, temperature, and weather patterns. One of the primary methods used to study exoplanet atmospheres is spectroscopy. When a planet passes in front of its star, some of the starlight filters through the planet's atmosphere before reaching telescopes on Earth or in space. Different gases absorb specific wavelengths of light, leaving behind unique signatures. By analyzing these spectral fingerprints, scientists can detect the presence of gases like oxygen, methane, carbon dioxide, and water vapor. The James Webb Space Telescope has already begun identifying atmospheric compositions of exoplanets with unprecedented accuracy, offering new insights into these distant worlds. Exoplanets experience some of the most extreme weather conditions imaginable. Many of these planets orbit so close to their stars that they are tidally locked, meaning one side permanently faces the star while the other remains in darkness. This creates enormous temperature differences, leading to supersonic winds that can exceed several thousand kilometers per hour. On planets like HD 189733b, powerful winds carry tiny silicate particles, causing glass to rain from the sky in horizontal sheets. Some exoplanets are so hot that their atmospheres contain vaporized metals. WASP 180b, for example, has clouds of iron that condense into molten iron rain. On other worlds, storms are not just intense, but last for centuries. On HD 106906b, enormous planet-wide storms churn through its thick atmosphere in a never-ending cycle. These storms may resemble the Great Red Spot on Jupiter, but on a much larger scale. While many exoplanet atmospheres are incredibly hostile, scientists are particularly interested in those that might support life. The presence of gases like oxygen and methane, especially when found together, could be a strong indication of biological processes. On Earth, most atmospheric oxygen comes from plants and microorganisms, while methane is produced by both geological and biological sources. If a distant exoplanet has a similar atmospheric composition, it could be a promising candidate for habitability. Future telescopes will revolutionize the study of exoplanet atmospheres. The upcoming Extremely Large Telescope and the planned Habitable Worlds Observatory will have the ability to directly image exoplanets and analyze their atmospheres in greater detail than ever before. These instruments may help scientists identify planets with conditions suitable for life, or even detect signs of biological activity. As our understanding of exoplanet atmospheres improves, so does our ability to identify worlds that may one day host human exploration. In the next section, we will explore the most exciting question of all: could life exist beyond Earth, and how close are we to finding it? When searching for life beyond Earth, scientists focus on a region known as the habitable zone, or the Goldilocks zone. This is the area around a star where conditions are just right for liquid water to exist on a planet's surface, neither too hot nor too cold. Water is essential for life as we know it, making planets in this zone prime candidates for habitability. However, temperature alone is not enough to determine whether a planet can support life. Several other factors influence a planet's potential to sustain life. A stable atmosphere is crucial. Without one, water would either evaporate into space or freeze solid. Earth's atmosphere, rich in nitrogen and oxygen, provides both protection and stability. Some exoplanets, like Kepler 452b, have been found in their star's habitable zone. But if their atmospheres contain too much carbon dioxide or lack essential gases, they may be inhospitable. A planet's magnetic field also plays a major role. Earth's magnetic field shields us from harmful radiation from the sun. Without it, solar winds would strip away our atmosphere, as happened to Mars. Exoplanets with strong magnetic fields could better retain their atmospheres, making them more likely to support life. Another key factor is radiation levels. Some exoplanets orbit red dwarf stars, which are common in the universe, but prone to intense solar flares. If a planet is bombarded with high-energy radiation, it could struggle to maintain life-friendly conditions. Despite these challenges, scientists have discovered several exoplanets that could potentially support life. Proxima Centauri b, orbiting the closest star to our solar system, is in the habitable zone of a red dwarf. However, its exposure to stellar flares raises questions about its ability to retain an atmosphere. Another promising candidate, TRAPPIST-1e, is part of a system with 7 Earth-sized planets, several of which may have liquid water. The sheer number of potentially habitable exoplanets suggests that life-supporting conditions might not be rare in the universe. Interestingly, liquid water might exist outside the traditional habitable zone. Some planets could have subsurface oceans beneath thick ice layers, similar to Jupiter's moon Europa and Saturn's moon Enceladus. Tidal heating from a planet's gravitational interactions with its star or nearby moons could keep these hidden oceans warm enough to support life. This means that even exoplanets far from their stars could could still harbour liquid water and possibly even life. Moons themselves may play a crucial role in sustaining life. A large moon can help stabilise a planet's rotation, preventing extreme climate shifts. On Earth, our moon helps regulate our climate and ocean tides. If an exoplanet has a large, stable moon, it could improve the planet's habitability. Scientists are particularly interested in exomoons, moons orbiting exoplanets, as potential locations for alien life. Future telescopes will be able to detect and analyze these moons in greater detail. To confirm whether any of these worlds are truly habitable, upcoming missions will focus on directly observing exoplanets. The James Webb Space Telescope has already begun analyzing exoplanet atmospheres, searching for biosignatures like oxygen and methane. Future missions, such as the Habitable Worlds Observatory and the Lunar Telescope, will provide even more detailed insights into these distant planets. These advanced instruments may allow us to detect not just potentially habitable planets, but even the chemical signatures of life itself. As we refine our search for habitable exoplanets, we edge closer to answering one of humanity's greatest questions. Are we alone in the universe? The next step in our journey explores the possibility of extraterrestrial life and the search for signs of biological activity beyond Earth. Super-Earths are among the most intriguing exoplanets discovered so far. These planets are larger than Earth, but significantly smaller than gas giants like Neptune or Jupiter. They typically have masses between 1 and 10 times that of Earth, and their diversity in size and composition makes them fascinating candidates for habitability. Unlike the planets in our solar system, which follow a clear division between rocky worlds and gas giants, super-Earths exist in a middle ground, displaying a wide range of characteristics. Some are rocky, like our own planet, while others have thick atmospheres or vast global oceans. One of the key reasons super-Earths attract so much scientific interest is their potential for habitability. With larger sizes and stronger gravity, many of these planets may be better at retaining dense atmospheres, which are essential for stable climates and liquid water. Some may have thick, protective atmospheres that shield them from harmful radiation, while others could host global oceans, providing a stable environment for life. The exoplanet LHS 114-OB, for example, is located in the habitable zone of its star and is believed to be covered in water, making it a prime candidate for further study. The variety of super-Earths is staggering. Some are entirely rocky, like Kepler 22b, which is thought to have a solid surface. Others may be dominated by thick, gaseous atmospheres, blurring the line between super-Earths and mini-Neptunes. Planets like Gliese 581c could be ocean worlds, with entire surfaces covered by vast, deep water layers. The diversity of these planets challenges our understanding of planetary formation and raises exciting possibilities for finding life beyond Earth. One important factor in determining whether a super-Earth is habitable is its gravity. A planet with twice the mass of Earth would have stronger gravity, making movement more difficult for any potential life forms. However, stronger gravity could also be beneficial, helping the planet retain a thick atmosphere that regulates temperature and protects against radiation. If a super-Earth has a balanced atmosphere with essential gases like oxygen and nitrogen, it could provide a stable and life-supporting environment for billions of years. Another critical factor is temperature. Some super-Earths orbit within their star's habitable zone, where conditions allow for liquid water. Others may have internal heat sources, such as volcanic activity or tidal forces, that keep their surfaces warm even if they are farther from their star. This means that some planets outside the traditional habitable zone could still sustain life beneath thick clouds or deep oceans. To determine if any of these planets could support life, scientists search for biosignatures, chemical markers in an atmosphere that indicate biological activity. The presence of oxygen, methane, and carbon dioxide in the right proportions could be a sign of life. On Earth, these gases are produced by living organisms, and their detection on an exoplanet could suggest a thriving biosphere. Future telescopes, like the Habitable Worlds Observatory, will be able to analyze exoplanet atmospheres with greater precision. potentially detecting these biosignatures for the first time. Upcoming research on super-Earths will focus on identifying the most promising candidates for life. The James Webb Space Telescope is already gathering data on their atmospheres, and future missions will aim to capture direct images of these planets. As technology advances, we may one day identify a super-Earth that not only supports life, but could even be more habitable than Earth itself. The possibility of finding a super-Earth with life-friendly conditions raises profound questions. If such a planet exists, could it host advanced life forms? Would its environment be similar to Earth, or would life evolve in completely different ways? These questions drive the search for habitable exoplanets and push the boundaries of our understanding of the universe. For billions of years, planets undergo dramatic transformations, shaped by forces as vast as stellar evolution and as subtle as atmospheric loss. Exoplanets, just like those in our solar system, are not static worlds. They evolve over time, sometimes becoming unrecognizable from their original states. Understanding how planets change over immense timescales provides insight not only into the diverse worlds beyond our solar system, but also into Earth's past and future. Planet formation is a violent and unpredictable process. Every planet, including those beyond our solar system, begins as a swirling mass of dust, gas, and rock orbiting a newborn star. Over millions of years, gravity pulls these materials together, forming larger and larger bodies. But this process is rarely smooth. Countless planetary embryos collide and merge, while others are flung into space or consumed by their stars. Young exoplanets are often extreme. Some worlds are covered in oceans of molten rock, while others are enshrouded in thick, toxic atmospheres. Massive impacts can dramatically alter a planet's composition, as seen in the case of Earth's own moon, which scientists believe formed from a colossal collision between a young Earth and a Mars-sized body. Similar events likely shape many exoplanets, determining whether they will have stable atmospheres, magnetic fields, or even liquid water. As exoplanets mature, they may cool down, form solid surfaces, and develop weather systems, making them more stable over time. However, not all planets remain in their original orbits. In many planetary systems, planets do not stay where they originally formed. Planetary migration is a process in which gravitational interactions between a planet and the surrounding disk of gas or other planets cause it to shift position. In some cases, entire planetary systems can be rearranged over millions of years. One of the most dramatic examples of migration is seen in hot Jupiters, massive gas giants that orbit extremely close to their stars. These planets likely formed much farther away before slowly spiraling inward. As they moved, they may have disrupted the orbits of smaller planets, sometimes ejecting them entirely from their systems. Some planets that were once in a habitable zone may have been pushed too close to their stars, turning them into inhospitable wastelands. Others may have been flung outward, freezing into barren ice worlds. Planetary migration is a key factor in understanding why some exoplanetary systems look so different from our own. While our solar system's planets have relatively stable orbits, many exoplanetary systems appear chaotic, with planets on highly eccentric orbits or packed tightly together. This suggests that planetary movements over time shape the structure of entire solar systems, sometimes in ways that make them completely unrecognizable compared to their early formations. A planet's fate is not only determined by its own characteristics, but also by the evolution of its parent star. Stars change over time, and these changes directly impact the planets that orbit them. As stars like our Sun age, they gradually become hotter and more luminous, causing their habitable zones to shift outward. A planet that was once in a comfortable, life-supporting position may slowly become too hot, leading to runaway greenhouse effects, as is believed to have happened to Venus. When stars enter their red giant phase, they expand dramatically, often engulfing their inner planets. Many exoplanets we observe today will eventually be swallowed by their stars, completely destroyed in the process. Others may survive, but will be scorched and stripped of their atmospheres. Some exoplanets may even outlive their stars. After a red giant sheds its outer layers, it leaves behind a white dwarf, a dense, fading stellar remnant. Some planets may continue orbiting these remnants, possibly harboring subsurface oceans or maintaining thin atmospheres, though their conditions would be drastically different from their earlier states. Atmospheric evolution is one of the most crucial aspects of planetary change. Over millions or billions of years, planets can lose their atmospheres due to stellar radiation, magnetic field decay, or large-scale impacts. Exoplanets that orbit close to their stars, particularly those around red dwarfs, are often bombarded by intense radiation and stellar flares. This exposure can strip away even thick atmospheres, leaving behind barren, airless worlds. However, planets with strong magnetic fields may be able to retain their atmospheres for much longer, shielding themselves from the worst effects of stellar activity. On the other hand, some planets may develop new atmospheres over time. Volcanic activity can release gases, gradually building up an atmosphere. Comet impacts can also deliver materials like water and carbon dioxide, helping to replenish lost gases. In some cases, biological processes, if they exist, could play a role in shaping an exoplanet's atmosphere, just as life on Earth has altered our own planet's air composition. A key question in astrobiology is whether life, if it emerges on an exoplanet, can survive long enough to evolve into complex forms. While some planets may remain habitable for billions of years, others experience drastic shifts that could challenge the survival of any life that may have developed. On Earth, life has survived ice ages, asteroid impacts, and dramatic shifts in atmospheric composition. If exoplanetary life forms are similarly resilient, they may find ways to endure even as their homeworlds undergo massive changes. One possibility is that life could migrate to more stable environments. If an exoplanet becomes too hot or too cold, life may move underground or into subsurface oceans, as some extremophiles do on Earth. In systems with multiple planets, life could even transfer between worlds via panspermia, a process in which microbial life is carried by asteroids or comets from one planet to another. By studying how exoplanets change over time, scientists gain a deeper understanding of the forces that have shaped our own planet. Earth has undergone dramatic transformations, extreme volcanic activity, mass extinctions, and radical shifts in atmospheric composition. Understanding how similar changes occur on exoplanets can help us predict what might happen to Earth in the distant future. One day, Earth itself will face the fate of many exoplanets. As the Sun ages, it will become hotter, eventually making Earth uninhabitable. Far in the future, our planet may lose its atmosphere and be swallowed by the expanding Sun, just as many exoplanets will experience with their own stars. However, the study of planetary evolution also raises another possibility. If humanity can anticipate these changes, could we one day move to another world? If we understand how planets shift and evolve, we may be able to identify a future home for our species, an exoplanet that could sustain life long after Earth becomes uninhabitable. The study of exoplanet evolution is more than just an academic pursuit. It is a window into the future of planets, including our own. By unraveling the mysteries of how planets change over time, we gain insights into the past, present, and potential future of life in the universe. Every exoplanet we discover is not just a distant world, but a story of transformation, survival, and the endless possibilities of the cosmos. For centuries, our understanding of planetary systems was shaped entirely by our own solar system. We assumed that most systems would have a similar structure: small rocky planets orbiting close to their star, followed by gas giants further out, all moving in nearly circular orbits. However, the discovery of exoplanets has completely changed this perspective. We now know that planetary systems can be far more chaotic, diverse, and strange than anything we once imagined. One of the most unexpected findings is the existence of planets with highly eccentric orbits. Unlike the nearly circular orbits of planets in our solar system, many exoplanets follow elongated, comet-like paths around their stars. This means they experience extreme shifts in temperature, freezing in the outer reaches of their orbit and then boiling as they pass close to their sun. The exoplanet HD 80606b, for example, has an orbit so stretched that it swings between deep space and a fiery close pass around its star every 111 days. Even more surprising is the discovery of star systems with multiple planets in the habitable zone. In our solar system, only Earth sits comfortably in this region, but exoplanet surveys have identified systems where 2 or even 3 planets could have conditions suitable for liquid water. The TRAPPIST-1 system, located just 40 light-years away, has at least 3 planets within its habitable zone. If conditions are right, these planets could have liquid oceans and potentially support life. Some exoplanets exist in even more bizarre environments, binary and trinary star systems. While our solar system orbits a single sun, many exoplanets have been found around stars that come in pairs or even triplets. Planets in these systems experience dynamic gravitational forces, which can cause unstable orbits, extreme temperature shifts, or in some cases, long periods of continuous daylight or darkness. The planet Kepler 16b orbits 2 stars, much like the fictional planet Tatooine from Star Wars. This means that if you stood on its surface, you would see 2 suns in the sky, casting eerie double shadows. Among the strangest planetary systems ever discovered is the HR 8799 system, which challenges almost every assumption we had about planetary formation. This system features massive gas giants orbiting at extreme angles compared to each other, suggesting a history of violent gravitational interactions. Another peculiar system is WASP-12, where a massive exoplanet orbits so close to its star that it is being slowly pulled apart by gravitational forces, with its atmosphere stretching into space like a trailing comet. Each of these discoveries forces scientists to rethink how planets form and evolve. The traditional model of planetary formation suggests that planets develop in a stable, orderly disk of gas and dust around a young star. But exoplanet studies reveal that many planetary systems are shaped by dramatic events, violent collisions, gravitational tugs from passing stars, or even entire planets being thrown out of their systems. Rogue planets, which drift through space without a star, may be the result of such chaotic interactions. These strange solar systems challenge our understanding of habitability as well. If life exists beyond Earth, could it have adapted to extreme environments? Could life survive on a planet with a highly elliptical orbit, enduring freezing and scorching cycles? Could it evolve on a world bathed in the light of multiple suns? The more we learn, the more we realize that nature is far more inventive than we ever imagined. With new telescopes and observation techniques, we are just beginning to uncover the full diversity of planetary systems in the universe. The coming decades will likely reveal even more surprising systems, ones that defy all expectations and force us to reconsider the very nature of planets, stars, and life itself. For centuries, humans have wondered whether we are alone in the universe. The discovery of exoplanets has transformed this question from speculation into a scientific pursuit. With thousands of confirmed planets orbiting distant stars, astronomers are searching for signs of alien life, whether simple microbes or advanced civilizations. But what would extraterrestrial life look like? Would it resemble life on Earth, or could it take forms beyond our imagination? The search for life begins with biosignatures, chemical markers that indicate the presence of biological activity. On Earth, life produces gases such as oxygen, methane, and carbon dioxide, which can accumulate in a planet's atmosphere. If a distant exoplanet has an atmosphere rich in these gases, it could suggest the presence of life. Astronomers use powerful telescopes to analyze starlight passing through exoplanet atmospheres, looking for these key signatures. Future telescopes like the James Webb Space Telescope and the upcoming Habitable Worlds Observatory aim to refine these techniques and provide more detailed atmospheric readings. But what if life does not resemble anything on Earth? Some scientists speculate that extraterrestrial organisms could be based on chemical systems entirely different from our own. Instead of water, they might rely on methane or ammonia as a solvent. Instead of carbon, they could use silicon as a structural element. Life may also exist in extreme environments, such as the scorching surface of a lava planet or the deep, lightless oceans of an icy exomoon. Studying extreme life forms on Earth, such as bacteria thriving in volcanic vents or frozen lakes, helps scientists imagine how life could survive on distant worlds. Beyond simple life, could intelligent civilizations exist on distant exoplanets? This question has driven the search for extraterrestrial intelligence, or SETI, for decades. SETI scientists scan the skies for technosignatures, signals or evidence of advanced technology. This includes radio waves, laser pulses, or even signs of megastructures, such as Dyson spheres, which hypothetical civilizations might use to harness the energy of their stars. So far, no confirmed signals of extraterrestrial intelligence have been detected, but the search continues with more sophisticated instruments and wider coverage of the sky. The study of exoplanets has also reshaped our perspective on the famous Drake equation, which estimates the number of communicative civilizations in the galaxy. Before exoplanet discoveries, many terms in the equation were based on guesswork. Now, with thousands of exoplanets identified, we have a better understanding of how common planets are, how many exist in habitable zones, and what conditions might support life. This has led some scientists to believe that life may be widespread, even if intelligent life remains rare. If alien life were discovered, it would mark one of the most profound moments in human history. Finding microbial life on an exoplanet would confirm that biology is not unique to Earth and suggest that life could arise under many different conditions. The discovery of an advanced civilization, however, would raise deeper questions. How would humanity react? Would we attempt to communicate, or would we fear the consequences? How would our view of ourselves change, knowing we are not alone in the universe? As technology advances, the search for alien life will only become more precise. Future space missions and telescopes will explore exoplanet atmospheres in greater detail, scanning for unmistakable signs of biology. Whether we find microscopic organisms or civilizations far older than our own, the answers we seek lie among the distant stars, waiting to be uncovered. The search for exoplanets has come a long way in just a few decades, but the journey is far from over. The next generation of space telescopes will revolutionize our understanding of these distant worlds, revealing details about their atmospheres, compositions, and potential for life. These advanced observatories will provide scientists with sharper images, more precise data, and the ability to analyze exoplanets in ways never before possible. One of the most significant advancements in this field is the James Webb Space Telescope, or JWST. Launched to observe the universe in infrared light, JWST is already transforming exoplanet research. Unlike its predecessor, the Hubble Space Telescope, which primarily observes invisible and ultraviolet light, JWST's infrared capabilities allow it to peer through cosmic dust and analyze the faint heat signatures of distant planets. This enables scientists to study exoplanet atmospheres in unprecedented detail, detecting gases such as water vapor, carbon dioxide, and even potential biosignatures. Its powerful instruments can determine the presence of clouds, storms, and temperature variations on exoplanets orbiting distant stars. Following JWST, the Nancy Grace Roman Space Telescope is expected to launch in the coming years. This telescope will specialize in wide-field imaging, allowing it to survey vast regions of space for new exoplanets. Unlike JWST, which focuses on detailed observations of individual planets, the Roman telescope will provide a broader view, helping scientists discover thousands of new exoplanets at once. It will utilize the microlensing method, detecting planets by observing how their gravity bends light from distant stars. This technique is particularly useful for finding exoplanets that are far from their stars, including rogue planets drifting freely through space. Another ambitious project on the horizon is the Habitable Worlds Observatory. Designed specifically for exoplanet research, this future telescope will take the search for habitable planets to the next level. Equipped with advanced coronagraph technology, it will be able to directly image Earth-like planets orbiting Sun-like stars. By blocking out the overwhelming glare of a star, the telescope will reveal the faint light of exoplanets, allowing scientists to analyze their atmospheres and determine if they contain the chemical signatures necessary for life. This observatory represents a major step toward finding planets that are not just habitable in theory, but could actually support life. Beyond these individual telescopes, the future of exoplanet research will also rely on next-generation ground-based observatories. Massive telescopes like the Extremely Large Telescope, the Giant Magellan Telescope, and the 30-meter telescope will provide even higher resolution imaging and more detailed spectroscopic analysis. These powerful instruments will complement space telescopes by studying exoplanets in ways that were previously impossible, such as measuring wind speeds in alien atmospheres and detecting volcanic activity on distant worlds. As technology advances, artificial intelligence and machine learning are playing an increasingly important role in exoplanet research. AI algorithms can process vast amounts of data more efficiently than humans, identifying subtle patterns that might indicate the presence of an exoplanet. Machine learning models are also improving the accuracy of exoplanet detection methods, helping to filter out false positives and refine our understanding of planetary compositions. By automating certain aspects of data analysis, AI allows scientists to focus on the most promising candidates for further study. The next decade will be a defining period for exoplanet research. With JWST already delivering groundbreaking results, the upcoming Roman Space Telescope and Habitable Worlds Observatory promise to push the boundaries of discovery even further. Combined with advances in AI and machine learning, these missions will not only increase the number of known exoplanets, but also enhance our ability to determine which ones may be capable of supporting life. As we look ahead, the possibility of finding another Earth-like world becomes more tangible with every new technological breakthrough. While thousands of exoplanets have been discovered, there are still many theoretical worlds that exist only in scientific models or in the realm of science fiction. Some of these planets could be real, but remain undiscovered, while others challenge the limits of what we understand about planetary formation and the conditions necessary for life. These hypothetical worlds raise fascinating questions about the nature of the universe and what may be lurking in the unexplored depths of space. One concept that has intrigued scientists is the idea of a planet entirely covered by an artificial structure, known as a Dyson sphere. Originally proposed by physicist Freeman Dyson, this hypothetical megastructure would be built by an advanced civilization to harness the energy of its host star. Instead of relying on planetary resources, such a civilization could construct a vast shell or swarm of solar collectors to capture nearly all of a star's energy output. If such a structure existed, it might appear as an unusually dim star, with only infrared radiation escaping from the excess heat generated inside. Some astronomers have already searched for potential signs of Dyson spheres by analyzing irregular dips in starlight, but no conclusive evidence has been found. Beyond artificial structures, there is also the possibility of planets where intelligent life has dramatically altered the environment. On Earth, human activity has changed the planet's climate, leading scientists to consider whether similar changes could be detected on distant exoplanets. If an advanced civilization modified its atmosphere through large-scale industrial activity, we might be able to identify unnatural levels of gases such as carbon dioxide, methane, or even engineered chemicals that do not occur naturally. These artificial biosignatures could serve as potential clues in the search for extraterrestrial intelligence, hinting at the presence of civilizations that have reshaped their planets in ways we can observe from afar. Science fiction has long envisioned strange and exotic planets, but some of these fictional worlds bear striking similarities to real exoplanets. For example, the desert planet Arrakis from the novel Dune is similar to some of the arid, high-temperature exoplanets discovered in close orbits around their stars. Similarly, the lava-covered planet Mustafar from Star Wars resembles the real-world exoplanet K2141b, which is believed to have vast oceans of molten rock on its surface. Even tidally locked planets, like the fictional world of Trisolaris in the three-body problem, have real-world counterparts such as Proxima Centauri b, which may have one side in perpetual daylight, while the other remains in constant darkness. Despite our growing knowledge of exoplanets, one of the biggest challenges remains the possibility of ever reaching them. Even the nearest known exoplanet, Proxima Centauri b, is over 4 light-years away, an enormous distance that would take tens of thousands of years to travel using current space technology. However, theoretical propulsion methods such as light sails powered by laser beams or antimatter-driven spacecraft could one day allow for interstellar travel at a fraction of the speed of light. Concepts like warp drives, often seen in science fiction, remain purely theoretical, but breakthroughs in physics could one day make them possible. As our technology advances, the line between science fiction and reality continues to blur. Theoretical exoplanets, artificial megastructures, and even planets shaped by intelligent civilizations remain speculative for now, but future discoveries could challenge everything we think we know about the universe. With each new exoplanet found, the possibility of encountering something truly extraordinary becomes more real. For centuries, humanity has gazed at the stars, wondering if other worlds like our own exist beyond the boundaries of our solar system. Today, we know they do. Thousands of exoplanets have been discovered, with many more waiting to be found. Yet, despite our growing knowledge of these distant worlds, the most profound questions remain unanswered. Can we ever reach an exoplanet? Will we one day build colonies on alien worlds? And perhaps, the biggest question of all, are we alone in the universe? As technology advances, our ability to explore exoplanets is entering a new era. Future telescopes, space probes, and even theoretical propulsion systems could bring us closer to answering these questions. The search for Earth-like planets is more than just a scientific endeavor. It is a journey that could redefine humanity's place in the cosmos. The discovery of exoplanets has accelerated rapidly since the early 1990s. In just a few decades, astronomers have catalogued thousands of worlds orbiting distant stars. However, most of these detections rely on indirect methods, such as the transit method, which observes a star's brightness dipping as a planet passes in front of it, or the radial velocity method, which detects tiny wobbles in a star's motion caused by an orbiting planet's gravitational pull. While these methods have revolutionized our understanding of planetary systems, they have limitations. The next generation of space telescopes will take exoplanet exploration to an entirely new level. The James Webb Space Telescope has already begun analyzing exoplanet atmospheres, searching for potential biosignatures such as oxygen, methane, and water vapor. In the coming years, the Nancy Grace Roman Space Telescope will conduct wide-field surveys that could uncover thousands of new exoplanets, including those hidden in regions of space where current methods struggle to detect them. Beyond these, ambitious projects like the Habitable Worlds Observatory are being developed to provide even greater precision in detecting and analyzing exoplanets. This telescope is designed to directly image Earth-like planets around Sun-like stars, something no existing telescope can do with high confidence. If successful, it could allow scientists to study exoplanet atmospheres in unprecedented detail, searching for conditions that could support life. Perhaps one of the most anticipated developments is the advancement of ground-based observatories. The extremely large telescope, ELT, set to become operational in the next decade, will feature a massive mirror capable of resolving faint exoplanets with remarkable clarity. By combining observations from space-based and ground-based telescopes, astronomers may soon be able to pinpoint planets that are not just habitable in theory, but potentially teeming with life. However, finding exoplanets is just the first step. The ultimate challenge lies in getting there. Interstellar travel remains one of the greatest challenges in physics and engineering. While science fiction often portrays faster-than-light travel as a routine method of exploration, the reality is far more complex. The vast distances between stars make even the closest exoplanets unreachable with current technology. Proxima Centauri b, the nearest known exoplanet, orbits the star Proxima Centauri, which lies approximately 4.2 light-years away. In conventional space travel terms, this distance is staggering. For comparison, the fastest spacecraft ever built, NASA's Parker Solar Probe, can reach speeds of around 700,000 kilometers per hour. At that speed, it would still take more than 6,000 years to reach Proxima Centauri. Clearly, if we are ever to travel to an exoplanet within a reasonable time frame, new methods of propulsion will be required. Scientists have proposed several theoretical solutions, ranging from laser-driven light sails to antimatter propulsion and even warp drives. One of the biggest obstacles to interstellar travel is energy. The amount of energy required to propel a spacecraft to even a fraction of the speed of light is immense. Conventional chemical rockets, like those used in modern space exploration, are entirely impractical for interstellar missions due to their low efficiency and fuel requirements. Nuclear propulsion has been proposed as a potential solution. Concepts like nuclear thermal rockets, which use fission reactions to heat a propellant, could provide much greater efficiency than chemical rockets. More advanced designs, such as nuclear fusion propulsion, could potentially push spacecraft to speeds approaching 10% of the speed of light. At such speeds, a journey to Proxima Centauri could be completed in just over 40 years. Still a long voyage, but within the realm of possibility for a future spacefaring civilization. Another concept gaining traction is the idea of laser-driven light sails. The Breakthrough Starshot initiative, for example, envisions launching small, lightweight probes equipped with reflective sails. These sails would be propelled by powerful Earth-based lasers, accelerating them to speeds of up to 20% of the speed of light. If successful, such probes could reach Proxima Centauri in just over 20 years, transmitting valuable data about its planets back to Earth. Even more speculative is the idea of the Alcubierre warp drive, a theoretical concept based on Einstein's equations of general relativity. This idea suggests that space itself could be contracted in front of a spacecraft and expanded behind it, allowing it to travel faster than light without violating the known laws of physics. While currently far beyond our technological capabilities, breakthroughs in physics could one day make such concepts feasible. Even if we were to develop the means to reach an exoplanet, surviving there would present an entirely new set of challenges. Exoplanets are incredibly diverse, and while some may resemble Earth, most are likely to have vastly different conditions. From extreme temperatures to high radiation levels and toxic atmospheres, finding a truly habitable world would not be easy. If a suitable exoplanet were discovered, the first step in colonization would likely involve robotic missions. These automated probes could survey the planet, analyze its atmosphere and resources, and determine whether it is safe for human settlement. If conditions proved favorable, the next phase might involve constructing habitats, either underground to shield against radiation or within self-sustaining domes equipped with life support systems. One key consideration would be how to generate food and oxygen. On Earth, these necessities are provided by natural ecosystems, but on an alien planet, artificial solutions would be required. Scientists have proposed using hydroponic farming, where plants grow without soil, as well as bioengineered algae that can produce oxygen while serving as a food source. Terraforming, the process of altering a planet's environment to make it more Earth-like, has also been explored in theoretical discussions, though it would require vast amounts of time and resources. Beyond the physical challenges, there are also psychological and social factors to consider. Life on an exoplanet would be isolating, with colonists cut off from Earth by years or even decades of travel time. Communication delays would make real-time conversations impossible, requiring new methods of long-distance interaction to maintain connections between the colony and humanity's home world. Despite these challenges, the idea of establishing a human presence beyond Earth remains one of the most exciting possibilities in space exploration. The first steps may be taken with missions to Mars and the Moon, serving as testbeds for the technologies that will one day take us even farther. As we continue our search for exoplanets and push the boundaries of space exploration, one question remains at the heart of our journey. Are we alone? The discovery of exoplanets has already reshaped our understanding of the universe, revealing that planets are more common than we ever imagined. Some of these worlds may harbor life, and perhaps even civilizations far more advanced than our own. If we ever do find evidence of extraterrestrial life, whether through biosignatures in an exoplanet's atmosphere or radio signals from a distant star, it will be one of the most profound discoveries in human history. It will challenge our understanding of biology, technology, and even the nature of intelligence itself. For now, our search continues. With each new telescope, each new mission, and each new breakthrough, we move one step closer to answering these age-old questions. Whether in our lifetime or in the distant future, the dream of exploring exoplanets, and perhaps even calling one home, remains one of the greatest frontiers in human exploration.